Welcome to our RSS 2021 Spotlight Talk, entitled STEP, Stochastic Traversability, Evaluation and Planning for Risk-Aware Off-Road Navigation. Estimating traversability and planning a safe path in challenging off-road environments is a difficult problem for an autonomous robot. Typical challenges can include rough terrain, slopes, overhangs, and narrow passages. On these types of terrain, robots can fail in various ways, such as getting stuck, slipping, or falling down. Typically, traversability is assessed in a deterministic fashion. Given sensor data, a cost is assigned to each patch of terrain. A threshold is set which determines what cost is considered too high for the robot to safely traverse. On the other hand, we wish to consider the probability distribution over the traversability cost, in order to reason about uncertainties which arise from difficult terrain, as well as localization and perception error. An average planner computes the average cost of traversal and makes decisions based on the mean of the distribution. While this approach is computationally efficient, it ignores dangerous tail risks. A worst-case planner, while safe, will tend to be very conservative in its paths. Planners which attempt to evaluate the full distribution of traversability costs tend to be computationally burdensome. In this work, we attempt to find a better trade-off between these objectives. Towards this end, we present a risk-aware traversability and planning architecture, which utilizes the conditional value-at-risk to perform rapid, uncertainty-aware navigation in dangerous environments. We begin by discussing our approach for processing an uncertainty-aware risk map. This risk assessment pipeline consists of many components, beginning with dense point cloud information from LiDAR or depth cameras. We perform point cloud merging, filtering, and ground segmentation. The ground points are used to construct a 2.5D elevation map. Next, we combine the risks arising from many sources. Importantly, we capture the uncertainty in the elevation map arising from localization and sensor error through an elevation variance model. We also account for a variety of other risk factors, including but not limited to collision risk, tip-over risk, and step risk. This leads to the question of how can we combine these different risk sources to effectively estimate the cost of traversing over an area. To answer this question, we construct a traversability model to give a random variable. We use this random variable as an input to a risk metric. Given the estimate rho of r at each point along the path, we calculate the path risk by composing the different point risks to get a single cost estimate for our path. In this work, we use the conditional value-at-risk as our risk metric. It computes the average of the tail of the distribution at a desired probability level for the tail. We assume the risk random variable is a normal distribution, such that the mean of that distribution is given by combining the various risk values from collision, step, and slope risk, and its variance is given by the sensor uncertainty estimate. This assumption allows for efficient aggregation of tail risks along a given path. Here we show the different risk sources for a legged robot navigating a challenging underground environment. The CVaR cost is computed for each grid cell in the 2.5D cost map. Next, we discuss the planning component of STEP. Our approach is motivated by the need to rapidly replan over a cost map which frequently updates as more information from the environment is added. Our approach relies on a hierarchical structure. We start with a geometric planner which plans a path in the range of 20 meters, minimizes the CVaR costs from start to goal, and does not account for the dynamics of the vehicle. The lower layer planner fully accounts for all costs, constraints, and dynamics. It plans in a horizon of 6 seconds and tracks the geometric path. To solve the complex kinodynamic planning problem at a high rate, we use Convex Optimization. We decompose risky regions into convex polygons. This allows for rapid convexification of non-convex obstacle constraints. We also convexify orientation constraints to reduce tip-over risks. The Kinodynamic Planner operates in the following steps. First, obstacles are convexified, and the path optimized for the previous time step is retrieved. Next, we create a library of randomly sampled paths, which will be used as an initial guess for the convex optimization problem. We also include heuristic paths among these initial guesses. We choose the path with the lowest cost as the initial guess, and optimize it by using a quadratic programming solver. Here we see the Kinodynamic Planner in action on a legged robot, as well as a differential drive robot in various challenging environments, such as abandoned nuclear power plants and lava tubes. STEP enables rapid and safe exploration at a desired level of risk. STEP has been extensively field-hardened over hundreds of kilometers of traversal in difficult environments and on multiple robots. It is the core traversability algorithm of the Nebula Autonomy framework, which JPL's Team CoStar used to compete in the DARPA Subterranean Challenge. This framework enabled a second-place win in the tunnel circuit and a first-place win in the urban circuit of this challenge.